Welcome back. Now that we have defined the maximum and minimum limits for dynamic range, let's go to the various dynamic range definitions that one can use in a receiver. I have to say that the specifics for the definition change greatly from one reference to another. So these are not the only definitions for dynamic range that you can find. But in general, there are two types of dynamic range that are used through the literature. One of them is the dynamic range limited by compression, and the other one is the dynamic range limited by intermodulation. And this is typically called the spurious free dynamic range. Let's see both of these. If we start with the definition of dynamic range, which is limited by compression. Using the diagram that I described before, in which we plot input power and output power, we'll have that the upper limit for the dynamic range is the limit for which the input power produces the 1 dB compression point. The lower limit for the dynamic range is the limit for having the minimum required signal. If this requirement for minimum signal is to satisfy a signal-to-noise ratio, that would be that would follow the formulas that we found before. However, often this minimum signal is set for a signal-to-noise ratio equal 1, right? At the output of the receiver, and therefore this minimum signal would be K TS plus TEB, right? It depends. Everything depends. It depends on how this minimum signal specification is defined, right? And often also the noise temperature for the antenna or whatever source we have connected at the input of the receiver, this noise temperature is set to T0, to 290 Kelvin. In any case, following this concept of dynamic range, the dynamic range would be the 1 dB compression point referred to the input minus the minimum required signal. And if you use the parameters referred to the output, then you would have to convert this, then you would have the 1 dB compression point referred to the output minus the gain minus the minimum required signal, right? So that would be the general equation of compression limited dynamic range. The other possible definition of dynamic range is called the spurious free dynamic range, and this is graphically shown in this graph. This graph again is the graph that plots the input power in dBm and the output power in dBm. And in this graph, I have plotted the lines that define the third order intercept. Now, the spurious free dynamic range would be defined as shown in this figure. Would be the range of powers going from the noise power given by this quantity, the noise power referred to the input, and that comprises both the power coming from the antenna or the source and the power due to the equivalent temperature of our element, of our receiver, right? There would be the limit, the minimum power at the input, and the maximum power would be bound by this S max, right? And at the maximum power, we would have that the intermodulation power at the output is equal to the noise power at the output. So the spurious free dynamic range would be, now if you analyze this, you will note that this distance x in here can be translated to this distance x in here. This distance x is the difference between the third order intercept point and the noise power at the output, right? If we translate this distance through this line, having slope 1 to 1, we find that this distance goes from here to here from the noise at the input, including the receiver noise, and the third order intercept referred to the input. This is X, right? Now, since this other line that has a 3-to-1 slope, we can determine that this distance in here would be X divided by 3, right? And therefore, the spurious free dynamic range would be 2/3 of this quantity, right? So again, the spurious free dynamic range is 2/3 of the third order intercept referred to the output minus the noise at the output of the receiver. And also again, we can refer this to the input, and it would be 2/3 of the intercept point referred to the input minus K TS plus TB in dBm. I have to point out that this spurious free dynamic range depends on the bandwidth of the signal, right? And it's important to point out that this is the bandwidth of the signal that we handle, not the system, right? And this is important because maybe our receiver is processing several frequency multiplex signals, right? And therefore, in any case, for every of these signals, the dynamic range will be different, right? In each case, we have to use the bandwidth for the noise bandwidth of the signal. By the way, this also applies to the dynamic range, the compression limited dynamic range that I've explained before. And to conclude, let me set an example, right? I put all these figures related to the dynamic range for an amplifier. This is a commercial amplifier having these features. The small signal gain is 26 dB. The noise equivalent temperature is 71 Kelvin. The 1 dB compression point is 10 dBm at the output, and the third order intercept is 20 dBm at the output. We will assume that the amplifier is connected to an antenna or a source having a noise temperature of 100 Kelvin, and the signal bandwidth is 27 megahertz, right? Now, let's see what the figures are for this specific case. Now, the noise referred to this input, to the input, that would be the noise coming from the antenna plus the noise due to the equivalent temperature of the receiver, would be close to minus 100 dBm, right? Minus 98 dBm, for example, right? Now, if we go up by 12 dB, which is the requirement in signal-to-noise ratio, that will give us the minimum driving signal at the receiver input, right? Now, going from the other side, from the top to the bottom, now we know that the third order intercept referred to the input would be about minus 5 dBm, which it would be 10 dBm minus the gain. And then this third order intercept, the difference between this third order intercept at the input and the noise is the quantity X, which is 92.7 dB, right? Now, 2/3 of this quantity is the spurious free dynamic range. So, from the definition of spurious free dynamic range, we would start from the noise referred to the input, and we would go up by 2/3 of this quantity, and that would be the maximum signal at the input that would limit the spurious free dynamic range, right? On the other hand, the 1 dB compression point referred to the input, it's this quantity, and this difference between 1 dB compression point and the minimum signal gives us the dynamic range. So, this power range in here, from here to here, would be the range of signal power at the input at which we satisfy the signal to noise ratio and in which we don't have gain compression, right? On the other hand, this power range between here and here is the power range at which the intermodulation, the power of the intermodulation products at the output do not go over the noise power at the output, right? And if you want to, there's some people do this, we can overlap this SFDR definition of dynamic range and this definition of dynamic range, and then we would have another dynamic range. This quantity of 49.8 dBs is the range of powers at the input in which we satisfy the requirements for signal to noise ratio, and we can ignore the intermodulation products because they fall below the noise. Some authors call this spurious-free dynamic range, right? Because I said the definitions are not there's not a unique definition across all possible references, right? So that would be the summary of the power levels and dynamic ranges that I have been described before. Of course, in this end of the scale, I've been describing powers at the input. You could do the same, exactly the same at the output, and it would be this blue scale at the output, which is exactly the same as the input, but shifted up by the gain of the device, right? And that concludes my lecture on fundamentals of transmitters and receivers. I hope it's been interesting for you. Thank you.